Okay, so here you can see the beginning of the Born-Oppenheim approach. The first slide with this red symbol uh, is the first equation with this symbol is a Schrödinger equation, but it is a Schrödinger equation only for the electronic part. So what we are doing here in the first step is we take a simplification. We say we look at the Schrödinger equation for the whole system, but at a fixed position of the nuclei. Okay, so I will make the following difference. There is the total electron wave function, and there is the total wave function of the molecule. So if I'm saying the total wave function of the molecule, it is a wave function that is a function of the coordinates of the electrons and of the nuclei. Okay, so here we first freeze the positions of the atoms. And for this frozen position, so now the atoms are fixed in space, we solve the electronic problem. And this is what's shown here in the first line with this diamond Caro symbol. So you can see there's the kinetic energy of the electrons, then there is the potential term, which describes the interactions of the electrons among themselves and the interaction with the nuclei. And this Wm, this is the corresponding eigenvalue, okay? So you can see this is already the full eigenvalue equation, but we have put the eigenvalue to the other side, and so we have this formula as it's written here. Note that this is an eigenvalue, so it's a real number. It's the solution of this Schrödinger equation, but you can think of it as a function of the coordinates of the nuclei. Why? Because for each position of the nuclei, you will get a different solution of the electronic problem. And if you repeat this for all kinds of possible arrangements of these atoms that form the molecule, you will get something which we will call, or which we have called already, the potential energy surface. So you see the potential energy surface is nothing but the eigenvalue of the electronic part of the Schrödinger equation for a given core arrangement. So this is Wm, and I've indicated it with M to show you that there is a whole set of electronic states. There is the electronic ground state, and then there are electronic excitations. And now comes the tricky part. If you just learn this from the slides, we make the following approximation, which is exact as long as we sum up over all electronic excited states. We can do the following. We can say we describe the total wave function of the molecule as a linear combination of our electronic wave functions, and the coupling coefficients themselves must also depend on R, on large R or R capitalized. Why? Because for each position of the nuclei or position of the atoms of your molecule, you will have a total wave function which is composed slightly differently of these electronic states. So to cover this, also our coefficients have to be a function of large R, of R capitalized. So with this assumption or with this equivalence, which is exact in the case where this basis is complete, we go now back into the Schrödinger equation. But this is the big step. So we just said this total wave function can be written in a basis of our electronically excited states, but in this linear combination, the coefficients themselves must depend on the nuclear coordinates in order to be able to describe any total wave function as a function of R and R capitalized. All right, now we go into the Schrödinger equation, but this time the Schrödinger equation for the total molecule. So we have the kinetic energy operator for the electrons, Te. We have the kinetic energy operator for the nuclei, and we have the potential term, which is a mixed term describing interactions of nuclei with electrons among themselves. And this E here, this excuse me, this is the eigenvalue of the total Schrödinger equation for the full system. And here, this expression is our way of writing the total wave function. So far, so good. This is all what we put in on tools, and now we work our way through by first multiplying from the left with phi n star. Technically phi n star because it's coming from the left. You had it in quantum mechanics, so we're in the dual space coming from left, multiplying with a corresponding basis function in this space of the electronically excited states. We just pick some arbitrary n for our derivation here. Okay, that's what's happening here. You come in from the left with phi n, and we integrate over the electron coordinates, meaning we integrate over r, small r. Right? So wait, give me a second. Are you still with me here? Mm-hmm. So could somebody write me quickly if you...
We are here, but you're gone.
Oh, okay, okay. So can you see the screen again? Can you see the slide 84 now? Please
No.
Yeah, okay, perfect. Thank you. Then I continue. So this is now our expression. Again, I used a symbol from Katz.
Wait a minute, we cannot see anything from your side.
Okay. Okay, I'll do it differently. So I'm sharing the screen now. I think
that works.
Yeah, I think this is a safer option. I won't use the option to combine PowerPoint and this, so I stay with the screen. I just show you then my current screen, and we just go through the slides in PowerPoint without starting the presentation. Okay, please. It's easier for me because the chat is then not visible when I'm doing this like this. If I'm gone or anything, please let me know acoustically this time. So just tell me I'm not sharing anything anymore, so that I know immediately. Okay, back to the slide 84. So we have this equation here now, and we do the following. We have multiplied from the left with this electronic eigenfunction phi n star, as you can see here. And now we take advantage of the orthogonality of the electronic states. So we know that if we integrate phi n times phi m over the electronic coordinates, we get this Kronecker delta nm. So we have only one if it's the same electronic basis function, and zero otherwise, because of this autonormalization of our electronic states, which is a result from solving the Schrödinger equation for the electronic states. Now, with this knowledge, we can simplify our expression for the total Schrödinger equation. If you look at the equation here, you see we have already made one simplification. Namely, I have taken advantage of the fact that phi m is an eigenfunction of the electronic part of the Hamiltonian. So we have replaced the kinetic term for the electrons and the potential term by this expression omega m of r. Okay, can you see this? The only thing that's left is the kinetic energy for the nuclei. Then comes the eigenvalue for this arrangement of nuclei, and then the actual eigenvalue of the total wave function. I go back one slide just to show you the difference. So here on this slide, you saw we had the kinetic energy of the electrons, kinetic energy of the nuclei, potential expression and the total wave function eigenvalue. And TE and TE and V, the potential, are now replaced by this eigenvalue here, because we already have solved the Schrödinger equation for the electronic part. And this is something we use here. So this is rewritten. You can see here TK is left, but we have here, I always say omega, I think I meant Wm for the potential for the electronic eigenvalue. So Wm of R is this electronic eigenvalue. Okay, now I can use the orthogonality of the electronic wave functions n and m as follows. We see Tk is an operator which contains derivatives with respect to the wave function, the nuclear wave function, which is here on the left-hand side. So we cannot so easily take this operator out and perform this integration. So this has to stay in. However, the other expressions in these brackets here, Wm of R and E, are not dependent on the electronic coordinates. Therefore, I can pull E, which is just a constant, and this potential expression out of the integral and perform this integral here, which gives me the Kronecker delta Nm. With this knowledge, I end up with this expression. So the only thing that remains is this integration over the Tk, and here we have a delta Nm. Now, the next step is to evaluate the Tk operator. What is it? It's the second derivative of a product which consists of the phi m and a chi m of R, right? So this is how it looks. And the second derivative, so we take the first derivative using the product rule. Then we take the second derivative, again using the product rule, and get these three terms. So now we know how this operator looks like, and we see what it does to the functions involved. With this knowledge, we go back and look now at this integral. So we put in for Tk our three terms, first term, second term, and third term. And now have a closer look at the third term. Here you can see this is the second derivative of chi m with respect to large R. So it is not affecting the electronic wave function, the phi. So in this case, phi n hits phi m without an operator, and the integration over the electronic coordinates gives us again this delta Nm. Okay? So here I can again pull out the expression from the integral and perform the integral, taking advantage of the autonomality of the electronic eigenstates. I cannot do this for the first and for the second part. Why? Because here I'm having a mixed derivative. This is the second order derivative of the electronic wave function. So the change in second order with a change of the nuclear position. So this is definitely some problem, because phi of m is a function of the electron positions as well. So I cannot really pull this out. And the same here, where I have a derivative of phi m, in this case just first order times the first derivative of the chi m with respect to large R. So only this expression can be integrated out in the electronic coordinates, giving me the delta Nm. So what I do now is I take this term and put it to all my other delta Nm terms, and in the overall integral, it cuts out the nth coefficient here on the left-hand side. You can see these were the terms Wn and E, which had the delta Nm before. This is the term that stems from the second derivative of the kinetic energy operator for the nuclei. So this is on this left side of the equation, and all the other parts, which are the two remaining parts of the second derivative, are on the right-hand side of this equation. Okay, this looks a little bit complicated because we have these mixed terms, but we can simplify this at least in the way we write it by simply defining that this right-hand side of the equation is our lambda nm. Now, this is simply a coupling element which couples different electronic states. Okay, this is the coupling element, because if this element, or if this right-hand side of the equation was 0, then we could solve the Schrödinger equation for each electronic state separately. Okay, but this is not the case because we have coupling terms as well. And now we come to the Born-Oppenheimer approach. The Born-Oppenheimer approach is simply setting the whole right term 0. Okay, so what we do is we assume that all these mixed derivatives are 0. And if lambda nm is 0, we effectively decouple all of the electronic states in the solution for the nuclear wave functions. So what does this mean? If we set this 0, you have a simple equation, which is written here, for this chi of r. And we introduce this chi of r as our coefficient in our basis set expansion of the electronic states. It didn't have a real meaning before because it was just a necessity in order to make it possible that the linear combination of the electronically excited states is giving me the total wave function. We had to introduce coefficients which are a function of r in order to make it possible to have a wave function as a function of r and r capitalized for any core geometry. And now, in this Born-Oppenheimer approach, we realize that these coefficients as a function of large r are our nuclear wave functions. Okay, this is now what comes out. These are nuclear wave functions. They are the solutions of a nuclear, or of the Schrödinger equation for the nuclei, given a certain potential energy surface. See, this is the potential energy surface which comes in. This is the electronic state n in its eigenvalue, basically. But we said the eigenvalue of the electronic solution depends on the core position. So for a different core position, I get different values for the different eigenvalue, basically. And this forms a function. And this function is our potential energy surface. Okay? And so what we are doing now, if you're interested in getting now the nuclear wave function, we have to solve this Schrödinger equation. And this is much, much simpler than solving the electronic problem. Because, for example, let's think of a diatomic molecule. We have an atom A and an atom B. Then the only coordinate that defines the overall geometry is the distance between atom A and atom B. Okay, so our eigenvalue is a function for the electronic ground state, a function only of the distance between the two nuclei. And this is our potential energy curve, which I have drawn on the blackboard several times already in the course of this lecture. So this is Wn of r. And in this potential, we have to solve now a Schrödinger equation. This is something you can even do on the paper. Why? Because this is you would do it typically on the computer with some finite differences method, for example, but you have a one-dimensional eigenvalue problem. You have given a potential function, Wn of r, and you try to find the corresponding wave function, which in this case is the nuclear wave function, giving, if you square it, the probability of finding the nuclei at a certain position in space. So in this Born-Oppenheimer approximation, our total wave function is now a simple product of this corresponding electronic wave function, phi n, times a nuclear wave function in this potential. And of course, since we have to solve an eigenvalue equation here, there are several vibrational states in this potential energy surface, which are indicated by this second quantum number nu. Okay, so the corresponding total wave function is simply the electronic wave function in this state, in the end state, for example, the ground state, multiplied with chi n nu, which is the nude vibrational eigenfunction in the potential energy surface given by the state, electronic state n. Okay, and this is our approximation in the Born-Oppenheimer picture. In general, we have non-negligible couplings here, so this is not really zero. And in this case, you will have not just a simple product of one electron function with one nuclear wave function, but you have a summation. You will have a coupling between different electronic and different vibrational states. I will show you now in a minute what I mean by this by drawing something on the computer. But I hope this is clear. Are there any questions so far? Okay, nobody's switching on the microphone. I think then I can proceed by, okay, I'm doing this old-fashioned now. I think it's best to stop sharing. So, okay, I've stopped sharing. Can you see me again now?
Yes.
Okay, perfect. Thank you.
Yes.
So, let me show you. Let me see how this works. Okay, I think this works. Good. So, I'll draw something for you. It is the potential energy surfaces that we were just discussing. Now, let's assume we have a diatomic molecule. So we have only this one coordinate, the distance between the two atoms. If I look at the energy E as a function of R, I get the typical potential curve. All right? And now I will have another excited state, which can be somewhere in range. I'll use a different color. So, give me a second. So, this is some excited state now. Okay, now you can see in both cases we have the energy as a function of the distance, and for both of these potential energy surfaces we can now use the Born-Oppenheimer approximation and solve the nuclear part of the wave function in these potentials. I'm showing this by indicating a few of the corresponding eigenvalues of the vibrational states shown as straight lines in this potential. Looks like this. Okay, so these are our eigenfunctions. You can see that in good approximation, if I'm not too far away from the minimum of this potential, which is the equilibrium distance, so the preferred distance between the two atoms, it's a harmonic oscillator. But then if you go to higher states, you will see a deviation from the harmonic oscillator as solutions of the nuclear wave function, because it's not a harmonic potential anymore. Obviously, it is a harmonic potential at the equilibrium, because if you do a Taylor expansion, this is the first element in the series, the quadratic, and then come the higher terms, which only play a role for larger for higher energies. Now, in this case, I just showed you the Born-Oppenheimer approximation is working. And now I show you a situation where the Born-Oppenheimer approximation will break down. Now look at this situation. I've added another state. Now this state is also higher in energy, but this state is not that high in energy in comparison to the energy of the ground state. And you can see that they are sort of overlapping. Or in other words, there are vibrational states in the ground state which are, if excited, in an energy regime where the molecule could actually also decide to be electronically excited. Okay, so in this case, our Born-Oppenheimer approximation breaks down because now definitely the two electronic wave functions are coupled. And I will have to solve the coupled situation, at least for these two states. So the good thing is that it is never more than 2, 3, 4. Yeah, 4 is already very, very rare. Interactions of states. So you never need all the electronic states, but it might be the case that two electronic excitations are so close that their energy difference is comparable to the energy difference you would get through vibrational excitation. And this is the criterion for the Born-Oppenheimer breakdown. If the energy difference for the electronic states is much larger than the vibrational energy differences, then it is safe to use the Born-Oppenheimer approximation. But if not, you will have to include both states that are interacting and have a coupled problem to solve, because then you have non-negligible coupling terms lambda nm, in this case for the first and the second state that I've shown here, so for the ground state and this excited state that I have just added. This is a breakdown of the Born-Oppenheimer approach, and in this case you even have the situation that for some energy, I will encircle this energy here, just as one point where it's particularly problematic because at this point, so for this internuclear distance, two electronic states have exactly the same energy. So obviously the total wave function must be a mixing of these two electronic states. Okay, I hope this made some things a bit clearer. I will switch back now to the slides and share. So, is my screen back on? Can anybody let me know, is the screen back on?
Yes.
Okay, thank you. All right, so back to the screen. On slide 86, you can see here a coupling element, an estimation for when the Born-Oppenheimer approach is valid and when not. What has to be fulfilled for it to be valid? And here you can see an estimate. You can see the coupling element that couples the two electronic states or the two vibrational states in these two different electronic states compared to the energy difference of the electronic states. Okay, so as I said, in these cases where electronic excitations are large in comparison to your vibrational states, you are safe in the Born-Oppenheimer coupling, and if not, then you will have to include several excited states. And now you also realize that the concept of a potential energy surface, so the idea that you can say, okay, when the molecule is arranged like this, then this electronic state has this energy, this concept is only fully valid within the Born-Oppenheimer approach. And it breaks down if we have two states two surfaces of almost same energy. They interfere, or they intersect, basically, as I showed you in this diatomic example. They intersect, and in this case, the potential energy surface for the ground state is no longer well defined, because depending on the geometry of the molecule, it's either electronic state A or electronic state B. So they start to mix, and we lose this concept of the potential energy surface. We still stick to the picture of the potential energy surface because it helps us to understand what's going on, but we have to accept that in this case, our electronic wave function is a mix of both. Okay, so that's what I wanted to say. Now you have for sure already heard about the Born-Oppenheimer approach, and you have read you can perform the Born-Oppenheimer approach in this case of the molecule because the electron mass is so much smaller in comparison to the nuclear mass, and therefore the rearrangement of the electron density is almost instantaneous in comparison to a change of nuclear geometry. This is correct, but it is a bit superficial because in some cases you have this coupling, and this is the case when you have this lambda nm terms being non-negligible, because then it matters what's your change in nuclear geometry, because it will substantially affect your electronic state. In these cases where all of a sudden, with a slight motion of the nuclei, the other electronic states gets lower in energy. Okay, so this is a deeper understanding of the Born-Oppenheimer approach, and I wanted to give you this at first because now we will discuss the electronic problem, which is so much more difficult than the actual nuclear problem, but we will always perform or take advantage of the Born-Oppenheimer approach and assume that it is valid so that we can decouple the problem and look only at the electronic problem for a given molecular geometry.